Good day to you. This is a seminar or webinar on introduction to wide bandgap devices. This is related to power electronics. So I am going to introduce a very new component of power electronics switch in the coming slides. I am showing you some images. These images were taken from Infineon website. The part is not commercially available. The symbol is slightly different from MOSFET symbol. This image is also taken from Infineon website. The power electronics industry reached the theoretical limit of silicon MOSFETs and now must go to another semiconductor material whose performance matches today's newer systems. The new material is gallium nitride, GaN, a high electron mobility semiconductor which is poised to usher in new power devices that are superior to the present state of the art. The new device is known as WBG, wide bandgap devices. So the following are the features or benefits of those devices. Elimination of up to 90% of the power losses that currently occur using AC to DC or DC to AC power conversion. These WBG devices offer high speed switching. So switching losses reduces a lot. Switching time, switch on time, switch off time may be in the order of 1 or 2 nanoseconds or maybe sub nanoseconds. The on time conduction loss is also very low compared to currently available silicon carbide or silicon based MOSFETs. So overall reduction in losses will reduce the heat sink size and hence the overall size of the unit. These devices can be operated 10 times higher frequency than silicon based devices, which will enhance high power performance and trigger multiple technology developments. Operating up to higher maximum temperature around 300 degrees C will provide better overall system efficiency, reliability along with size reduction. WBG semiconductors are expected to pave the way for exciting innovations in power electronics. Operation at higher frequencies than silicon based devices, making possible more compact, less costly product design. This is a hush braid designed by me. This can operate up to 1 kilowatt. That is 1000 watts, but in the same MOSFETs, this H bridge based on MOSFET, the same MOSFETs are replaced by high frequency WBG devices, and then I can enhance the power level up to 10 kilowatt. This is the estimated figure, 10 kilowatt, and I may have to replace the driver IC suitable for WBG. Then the same size can accommodate up to 10 kilowatt H bridge. As manufacturing capabilities improve and market applications expand, costs are expected to decrease, making WBG based devices competitive with less expensive SA based devices. Check the price, but the company is not available. The price, quoted price is around 600 rupees for a device of 600 volt and 26 amperes. Gallium nitride is grown on top of a silicon substrate. The end result is a fundamentally simple, elegant, cost-effective solution for power switching. This device behaves similarly to silicon MOSFETs with some exceptions. I'm not aware what are those exceptions. I need to study more. Maybe I may be making another video about how to drive these WBG based devices. 2 types of switches are available, normally on and normally off, but we are always used to use devices of normally off type. That is depletion mode GaN devices. Devices have started appearing in the market. They are available in DigiKey. For more details, check this link. EPC is one of the manufacturers of such devices. Infineon is also coming up with some devices, but those devices are not yet commercially available to buy. Pricing also seems to be affordable. 350 volt 26 ampere MOSFET based on WBG is priced till extra rupees 600 in low volumes. Besides its low RDS-on, the later structure of the enhanced GEN MOSFET also makes it very low capacitor device. So it can switch hundreds of volts in nanoseconds, giving it multi-megahertz capability. It is possible to operate around 30-33 megahertz. These switches can be operated around 30 to 33 megahertz also. The PE2900 from Paradigm Semiconductor, now PSemi, is an integrated high-speed driver intended to control the gates of external power devices such as enhancement mode gallium nitride transistors. The output of the PE2900 are capable of providing switching transition speeds in the sub-nanosecond range for hard switching application up to 33 megahertz. So this is the block diagram of that driver IC for WBG devices. The layout is most critical. All of the devices switch extremely fast and therefore the parasitic inductance of the layout must be as small as possible in the range of 0.4 nanoyard to 2 nanoyard is desirable. Cree, now Wolfspeed, has come out with a device of 300 amperes or 1.2 kV off-bridge module packaged in industry standard 62 mm housing. The module reduces energy losses 5 times than compared to the equivalent silicon solution. This efficiency enables an all SiC high power converter rated up to the megawatt level. SiC stands for silicon carbide. So this is also coming up well. But gallium nitride offers superior performance even compared to silicon carbide based devices. This new device will trigger development in other areas. For example, we need to develop high frequency inductors and transformer. This will again trigger development of new core material. We also may need low ESR capacitors of all values suitable to withstand such high frequency and high current. PCB fabrication techniques may need improvement to offer low stray inductance. Components may need to be mounted in a 3D array to reduce stray inductance and capacitance. So this brings to the end of our presentation. Thank you very much for watching this video.